So I remind you the theorem that we were proving since it is this theorem by Berlin, which says that suppose that lambda is a sequence of real numbers which is separated and then what we proved actually yesterday was that if lambda is interpolating for the polylinear space with spectrum minus half over 2, minus a over 2 over 2, then with the upper Berlin density is less or equal than A. And then what it remains to prove today is that if lambda is sampling, again for the polynomial space, then the lower Berlin density is bigger than alpha. Okay, and this reflects, I think, the idea that if you want to be able to reconstruct your function from the samples on a set, this set cannot be very sparse. You have to have at least some number of points in each interval. And if you want to be able, for every sequence on to be able to interpolate, then you cannot have too many points. You may have your points that could be a little bit sparse so that you have to interpolate. So we proved that part, and we managed to prove this one. Again, the idea is very close to what we did yesterday. Remember, yesterday we said, okay, interpolation means that the corresponding system of kernel vector is a RIS system. We constructed the dual, we had some relation, we integrated the relations, and so on. So the idea is very similar. So we sampling by definition. I remind you something by definition. It means that if I consider this system of kernel vectors, this system is a frame for this Hilbert space. Okay, and a frame means that I have this operator. So it's some kind. It's two inequalities, but it's just to say that this operator which maps the polylinear space to little L2 transcends a function x to x from G n is bounded above below. This is still a definition what the frame is. So the definition of what it means. And remember, we had this lemma, which I will use sometimes. They said that this is a Hilbert space fact. If P is an operator from some Hilbert space to another Hilbert space, then P is bounded above and below if and only if these are in subjective. Okay, this we proved some weeks ago, and the point is that this operator has an adjoint. So furthermore, by this lemma, sampling is equivalent to say that this operator, let's call it T, which goes from L2 to A and maps AN to linear combination of D and AN is bounded and when I say bounded, I mean maybe this is not a priori defined for all sequences A and L2, but what it means is that if you define it for sequences which have finitely many non-zero terms, then you have a bound uniform independent of the number of terms which are non-zero, and then you can extend it continuously to the whole of a little element. This is pretty much what we already know about sampling, and the corresponding tool we need from Hilbert space theory, which corresponds to the dual risk system, is the dual frame. So here I was saying the things are not so smooth in the sense that so in general you cannot, if you have a frame in a Hilbert space, you cannot have another frame which is bi-orthogonal to it always. So for example, by orthogonal I mean this relation. For example, take little 2 and take the following sequence. So this EI are the standard orthonormal basis for little 2. This is a frame. Actually, is what is called a tight frame, because if you take D1, if you take GI 8, GI, and you sum all GI, this is exactly equal to 8, E pi. Maybe I need the squares. Yes. Okay, which is just the normal 8 in little 2. So it's not only a frame, but it's actually the lower and the upper bound is 1. But of course, we cannot have a bi-orthogonal system to it, because if it's orthogonal to the first vector, it's going to be if it's orthogonal to all but the first vector, is going to be also orthogonal to the first vector. So you cannot, because this is the same vector. So you cannot have a bi-orthogonal frame in general. So we have to weaken a bit what we mean by a dual frame.
Can you repeat why it's not dual?
So imagine this is your frame G1, G2, G3. Imagine I have a frame which is bi-orthogonal to this one. It means that F1 paired with G1 with 1 and F1 paired with G2 is 0. But these are the same vector, so this cannot happen. Of course, this is not the case for a RISC system, because this is not a RISC system. RISC systems are formed by linearly independent vectors. This is not the case for frames. You can have repeated vectors and so on. We don't have this bi-orthogonality relation. and we have some kind of substitute which for our purposes is
finite dimensional phenomenon.
it's it's three-dimensional. It's in the plane terms. Suppose that actually you can prove, if we don't even need it, but you can prove that if a frame has a bi-orthogonal frame, then it's a Riesz basis. So the only case that you can actually find the bi-orthogonal frame is when you are already a Riesz basis of the space. So really you cannot do it unless you are in the previous case of the Riesz system. Suppose that GM is a frame. Then frame and that's that. So we keep some of the in fact we keep some of the properties that we had for the dual Riesz system. In particular, this frame has this property that we can express any vector in the space using this functional as the coefficients, and this holds for space. Remember, in the Riesz system here we had the projection of data from the space where the GN span, but GN are dense when you have a frame. Exactly. So and we need the second property, which to me, when I read it, it looks very arbitrary, but we need somehow. You at least keep some of the. You don't have the orthogonality, but you have the fact that when you pair the same Fn with GM index, you don't get something. You get something which is less than 1. In fact, not a constant is not enough for our purposes here. We need 1. So this is the abstract thing we want to prove. I don't know. So notice that we have 3 claims here, right? That Fn is a frame. And it satisfies 2 conditions. And I don't make any claim about uniqueness. You might have many dual frames which satisfy these conditions. We are going to construct one, but there are others. So it is useful in the proof to keep this notation for these operators that are associated with frame. So remember that F was the operator from A to L2 stands X to the sequence of the coefficients, and T was the operator from L2 to A sends a sequence. And this, by our hypothesis, this is bounded, let's say, above and below. And this is subjective and non. Okay. The idea is the following. You consider, and of course, P is the S star. Okay, these are what I mentioned. Okay. And the idea is the following. So remember, we want to construct an object which is not unique, so some artificiality has to enter into the construction. So we take the composition of these two operators, which goes from 8 to 8. So we take F here. And TF is T. Okay. So it's positive self-adjoint. What I want to say is that, okay, it's bounded, it's a composition of two bounded operators. I want to also say that it's bounded below, because if I know that it's bounded below, its adjoint has to be surjective, but the adjoint of it is itself. So it has to be also surjective, and it's going to be an isomorphism. So take an element in the Hilbert space. Then up to some constant A, which depends on the frame Gn, the norm of 8 is less or equal than the norm of S is squared. Okay. Is the definition of this being bounded below. But this is F8, F8, which taking the adjoint is TS8. And by considerably less or equal than the norm of TS8 times the norm of 8. Okay, so this proves, in fact, that this TS is bounded below by simplifying the case. And now this argument runs, TS is bounded below and above. Its adjoint is surjective, but its adjoint is itself. So TS is surjective and it's bounded above and below, so this is an isomorphism. This Hilbert space is isomorphism. By the way, in the literature, this operator is sometimes called the frame operator. We can, let's say, pull back this Gn. So we have some candidates. Okay. For which the Fn could be. Okay, I want to prove that this is the right choice. It is one right choice for the Fn. So we have to prove, yes. So we have to prove that it's a frame, first of all, and then prove the two properties. And to prove that it's a frame, I have to prove that the S operator corresponding now to the system Fn is bounded above and below, or equivalently, that the T operator corresponding to Fn is subjective. It's easier to show the latter. So let's say that T this T F is the operator which goes from 7 to 8, and then A then to the point is that I can write this operator in terms of the T and S of the system Gn, and then it will be clear that this is bounded objective. This is because take, for example, an AN sequence, which is has finitely many non-zero terms, and then T f of this sequence AN is by definition AN Fn. But this is T s minus 1 of AN given, and it is T as minus 1 of T of AN. Okay. And now it's so that the TS operator is T as minus 1T. So it is bounded because it is a composition of bounded operators. T is surjective, okay, and Ts minus 1 is of course surjective, it's a bijection, which proves that also Tf is surjective. Okay, so this proves that Fn is a plane. What it remains to prove? Let's see. It remains to prove it. First, you have this reproducing relation and this property. Okay. Yes. So consider as we said, yes, let's see. I'm going to use this relation, right? T, the operator T associated with the system F is this one. So the operator S associated with the system F, which sends a vector to its Fn, is the adjoint of this one, right? By definition. Is that this part is self-adjoint, so it's just T star this operator. But this star is S. And then it's just suffices to see that if I consider this quantity, this is just T of the sequence A. Okay. Again, by the definition of T, it sends a sequence to the linear combination of the sequence with the GNs. Okay. But this sequence is just FPS minus 1. apply to X. Yeah, PS minus 1 apply to X, and then this case apply to X. Okay. Yes. And the last one. So what is Fn GM? By definition, Fn was yes minus 1 to Gn, or I can write Gn as Pn Fn. I move the adjoint, so I get the norm of Fn squared. In little, which is Fn, comma Gn squared. F is the operator associated to the frame Gn. By definition. And now it suffices to notice, of course, this means that this is a positive thing. But this term appears somewhere in this infinite sum squared. Okay, it's the nth term of this infinite sum. So in particular, if I subtract it, I get still something positive. Which of course can happen if and only if this is less than 1. Okay. So this is yes, the construction of the dual frame. By the way, this frame constructed in this way is sometimes called the canonical dual frame. But yes, as I said, there are other dual frames which you can use. And from here we can go back to the Paddy inner space and prove the density theorem. I think what it's worth keeping from this frame or risk-based theory is that for each system of vectors, you have two operators, F and T. Frame is the F operator to be bound above and below. Risk is the T operator to be bound above and below, and then everything comes by duality. You don't have to think. So we have the exact analog of this lemma that we showed yesterday for the Palladian space. It says if Fn G Gn is a plane, then it's dual as constructed there, the canonical dual set. Then this sum is constant equal to n for all x. And the proof is again very similar to exactly identical to what we did yesterday. You have the sum, you write G of x as Gn paired with the kernel vector, the same for Fn. And then you use, we want to use this property. So what we do is that we bring this number inside there. And this is the norm. This is by the fact that this is the dual plane Gn, this is the norm of kxa. This is kxa, and this is the norm square. A. In linear space. So this is really the same. Again, because frames are spanned the whole space, you get exact equality, you don't get inequality. Now, for the proof, there is same. So remember, yesterday we started with some with the observation that all this in the Palladian space, all these kernel vectors can be written as a translation of one function. So this is the proof of the theorem. This is the proof, yes, proof of the second part. Yes. And this was a crucial observation. Among other things, we said so fixed sum epsilon positive. We said we worked with this function alone. We said I can find some b of epsilon positive such that if I integrate far away, this is smaller than epsilon squared, and this we can still do, and we will do. Only this time we need another estimate. So that b is chosen so that this holds, but we want also it holds which is for the observation. that so if I sum now over samples, this function, this is also smaller than epsilon squared, uniformly in X. So I mean that I can choose B independently of X, such that this follows for all of X. Okay. This is because of the decay of the function G. Okay. So G X was like that's wrong. The single function P and A X. Okay. In particular, I have some decay at infinity. I can say that g of x is less equal than some constant that depends on A times something like square root of x squared plus 1. So it decays like 1 over x is infinity. And this is only a size condition. I don't really have to find things about the behavior of G. I mean, just need a crude estimate on the decay of G. So what I'm saying is that this quantity that I want to estimate this quantity here with another star. I hope I don't make you confused with the previous star.
You need a separation, right? Yes.
I need a separation here, yes. It's a calculus thing if you have a separation, yes. The point is that so what I need to estimate is that is this thing and the point is that if you have a separation, then you can pretty much compare this thing with the integral of 1 over x squared plus 1 away from B. That is because here is your x. Here you exclude all lambda n in this interval, and you are summing just over lambda n that are outside this interval.
So we mean that we compare the series.
Yes, because moving x, you compare with the series.
Okay.
Yes. So the way I formalize it is that since you have the separation, let's consider only lambda n that are on the right hand side.
Yeah.
So consider lambda n. Okay.
Yeah.
And my function is something like this. Okay. I can find a delta such that these half intervals are disjoint. So these are the intervals. And in fact, if I multiply and divide by epsilon, then this is exactly the area of these rectangles, which are disjoint and lying below the graph of the function. So this is less or equal than 1 over epsilon times the integral from the furthest point you can be is x plus b minus epsilon to infinity. I don't know, dy. But this, now the point is that this does not depend on x. Okay, so now by taking b large enough, you can make this one. And here, yes, you have the separation. Of course, it's symmetric completely to the left side in the same way. So this you can do uniformly for all x. This you can do on. And now we try to put these things together because we know that A is the sum over all n lambda g and and I play the same game. I consider almost the same game. I consider an interval I where I want to estimate the number of points. This time I make two perturbations of the interval. I take one, which is, so suppose this interval has a length r, then I take this smaller one, let's call it I b, to have length r minus 2b. So I shrink it by I keep the center and I shrink it by b on both ends. And I take, as I did for the interpolation, I with and it's b to be the same a lot by b. So this is b. And then you have v and b one. Okay. And I split the sum on three regions. Okay. First, I consider the n such that the lambda n is in the smallest interval. It's the same. All the sort of difference. I put the difference in the order that I put in the notes here. First, I consider what is away from everything. Okay. R minus I b. Here I sum the same thing every time I do it. Okay. Then let's say what is the main part is lambda n, which lie in the small interval. And then I consider what lies in this small relative. I need, remember that I need to estimate the density from below. So here I need to estimate these three things from above in terms of the number of points in order to have the estimate from below of the density.
The upper lower increasing returns here, which
Yeah,
Yeah. And here is
yeah,
correct this. So yes, let's see. A is what is far away. What is far away should be controlled by this condition. We cannot go. It's- So these are all things that depend on X. So what I really want to do is like I really need calculation to integrate over time and estimate things. So here I just do 2 times the Cauchy Schwarz inequality. And I get that this is less or equal than the sum over all n. Here again, the integral of g. Times the same thing for Fn. Again, lambda and p. So yes. Exactly. So the third part what I want to say for the second part. Do I get the number of points? No. Okay, so for this, the sum of f and x. Right. This is I will use the property that this is a frame bound. Okay. I write fn of x as fn paired with the kernel, but this by the property that fn is a frame, I know that this I can bound this by a constant times the norm of k x a squared. So it's c times a. So what I have there is just the integral of the constant function. So I get for the second term with the integral, I get just the length of the interval at the power 1/2. So if I integrate. And for yes, for this one. The no, here there is no square root. The square root appears when I put it in the. So I want to gain another square root of the interval from this term. Gn was Gn minus 1 square. And here I find Ah, yes. And let's see. Yes, I think I should use again the property that Gn is a frame. Yes. So I do the same trick here. Okay. So only now that I need to here I ignore the set where I sum over. Here I want to be more careful. This is lambda n in is it?
Yeah.
Should be that one.
Well, that's a uniform in the X.
Yeah. I don't know why I was sorry. I was convinced I had to use the first one. So it is, yeah, in fact, it is the second one, exactly. So this is less than, yeah, this was even easier to estimate. It's less than epsilon squared. And when I make the integral over I, this is less than epsilon squared times the integral on I. So in total, what I have, the integral of the first part is less than epsilon times the length of I. I made it more difficult than it should be. Times the constant with yes. So B, which is my main term, so it is the sum of B integral. Now I use so here the idea is the same as interpolation. This integral I write as the integral on R minus the integral of the complement. So it is the inner product of f and gn minus the integral in the complement. But remember, this is the positive number less than 1, by the way that we constructed the dual equation. So this is less or equal than the number of points in IB. Yes. Minus B. I can even put, sorry, I can even put triangle, put the absolute values here. And yes, and this I estimate again in the same way I estimated the interpolation.
R minus 5, no.
Minus. So this is the estimated integral. It is less than the integral and times the normal section. This is an integral on I, when 5. And from this condition, exactly as we did in interpolation, this is smaller than epsilon. And F can have uniformly bounded norms because it is a plane. Some C. Epsilon. So in total, when I sum, I get that the integral of B x over I is less or equal than 1 plus and the constant like epsilon, the number of the points that I have in I. And then the last one. Now we can erase these two assumptions so that the last one is really it should be easy because this length, the length of these two intervals that I consider here is that the constant thing is 2b. So by separation, so I just throw away Zn and head by their maximum value. So this is so equal to times the number of points that I have there. But the number of points that I have there is that I have an interval of length 4 times b, two intervals of total length 4 times b, and divided by the separation constant of the points. You cannot have more than this number of points in there. And this is another constant times times b over that. And now integrating is now I just need to put everything together. So I know that A is smaller than these three sums. So one was an epsilon times the length of I, let's say R times C. The second one was 1 plus E times epsilon times the number of points in the class. And the last part was just
And if the point, what is this supreme?
wait, it's finally supreme.
Oh, because I is not.
Yeah.
Doesn't it?
What? No, what's the question? Why is the supreme of the function finite?
No, on what it depends. Okay, we go for Gn. Yes. For Gn. Oh, we could also be Fn. I don't know.
Fn is a frame. And then every frame has uniformly bounded norms. Wait a second.
In terms of
Subnorm is always in the polylinear space. The subnorm is bounded by the norm in the real line.
all right, you have to find it.
So this sum is so the terms in this sum is the number of points in this interval. This interval is the interval of length 4 times b, and we have a separation constant delta.
Yeah, that's true. No, because that supremo really is a supremum over x and over n, right?
Yes. Yeah. So every in the polylinear space, every function has modulus which is on the real line is uniformly bounded by the norm. By this what
yes.
yes. Okay. On the real line. And Fn and Gn are frames, and frames have uniformly bounded norms.
Okay.
So you're right, but
Okay.
here it's a soup over everything. Okay, and so I integrated over I, so I get also an I here.
B should be B. This is
And so let's see, I want to estimate this thing. I want to divide by the length of I.
yeah.
So what's
Mhm.
I'm sorry, yes. This is not a good estimate. I want this to go to 0, so it's better if I just estimate by the norms. I think, yes. Sorry, this is, yeah, this will give me a constant that if I let the length of I go to infinity, this an epsilon is negligible, also this, but here I get a constant term. So I need something which is better than this estimate, and then I can do as follows. Sorry about that. Yes, so when I integrate over I, this is that smaller than, so each of these things is smaller than the norm of Gn times the norm of Fn, because it's bad. And here I have the number of points in the, so the number of terms, and each term is smaller if I just integrate over R here. Because it's backed by the norm of Gn and the norm of Fn in the final limit. But these are uniformly bounded because these are frames. So you get this thing which does not depend on I. Now it's much better because I have something which goes to 0. Right. So now, sorry, my estimate was correct, but it was not good enough.
Yeah.
So I
Are you don't have I anymore, right?
yeah, I don't have I. And I is big. It's not something that's
Okay.
yes. And this now it's now I take the length of I to go to infinity and find it.
No.
Okay. Here's the ID, but it's not. It's the same thing because in the difference of the points is a finite number of points that balances as what I goes to. Okay, that was the group. That was pretty much all I wanted to say. I wanted to give you some references for these things, if somebody's interested. So I think the two standard books on sampling and interpolation is one is by C. These were in fact some lecture notes that became a book. And it deals with the hardly the space on the disk and on the space of entire functions as well. But it's a very short one and quite dense. And then there is the one which is more concentrated on the peak spaces and peak interpolation, which is by Angelo McCarthy, peak interpolation and simple function space. And if I didn't mention, this proof is from Violevsky and Nilsson from a paper called Revisiting Landau's theorems. For the Palevina space. In fact, they say Landau because what they prove, and you can, if you look at the proof, you can see that it works the same. Instead of, so Palevina space was a space of functions, of Fourier transform of functions supported in minus a over 2 and a over 2. Okay. But you can define a Palevina space associated to any closed set, let's say. You can say the Palevina space of a set S is Fourier transform of function supported on the vector S. And this proof goes through the same to show that the density, the lower density is bounded by the measure of S, and the upper density is bounded by the measure of S for interpolating sequences for some distances. So this was originally a generalization of Landau of the theorem of Berlin, which only applied on the integral. That's why they refer Landau to this theorem. That was all.